Okay, here's a video solving two practice problems that you'll be putting in your notes. These are from the PowerPoint on rotational motion. So here we're going to have a ball that is being swung in a vertical circle. So like this. And the radius of the string is 0.45 meters, and the mass of the ball is 0.5 kilograms. And we're trying to figure out how fast do we have to spin the ball in revolutions per second in order for the ball to not fall downward at the top of the swing. All right, so you can imagine that this is being swung, if there's a person right here, it's being swung vertically like this. It's a vertical swing. Okay. So what we have to think about here are the forces that are going on. From the previous video, we know that there is centripetal force going downward, and then there's this sort of fake centrifugal. I'm gonna leave them both as F sub c, just with different colors. And there's a centrifugal force going outward. And also from the previous video, we saw that this is true, that the way you calculate these two forces is the same. Okay, so we're trying to get the ball to not fall down at the top of the swing. So let's just sort of zoom in of this ball at the very, very top of the swing. So let's just say that this is the ball at the and it's going like this. Just, obviously it's going in a circle, but at that very, very top moment. Well, there are two things going on here. One is gravity is trying to pull this ball downward. And we need to spin this thing so fast that this centrifugal force, the fake force, but the centrifugal force is going to counteract gravity. So we need to set these two forces equal. We need to say that, that's fine. We need to set F sub c equal to, equal to the force of gravity. I was jumping ahead a step there. Which means we need to set the centrifugal force equal to mg. All right, the mg is trying to, the gravity is trying to pull this thing downward. We got to spin it really, really fast, so that centrifugal force counteracts that. We know from this earlier idea that even though centrifugal force is a fake force, we can still calculate it using the equations for centripetal force. And the reason, one more time, that we can do that is because if you notice this ball, it is maintaining, I'll go darker here, as it travels around here, the r, the distance away from the center, is always staying the same, which means it's not accelerating inward and it's not accelerating outward in terms radially, which means that this green force, the centrifugal force, and this blue force, this centripetal force, they must be equal. So we're going to be able to calculate the centrifugal force using the equations for the centripetal force. And this is something we're going to do all the time. So we're trying to get this answer in revolutions per second, which means that we're most likely not interested in the tangential velocity. We're more likely interested in the angular velocity, right? We're more interested in that. So let's use that equation. Again, it doesn't matter. You could solve for either, but then if you solve for v sub t first, you're just going to have to convert it anyways. So let's just solve it straight away for mr omega squared has to equal mg. Hey, guess what? Mass doesn't matter. You could be spinning a car for all you care at the end of the string. The mass is irrelevant. You would have to spin that car at the same rate as you would have to spin a ping pong ball to keep the car from falling. And again, that's a really interesting thing about physics, is how often the mass of objects is irrelevant. So r omega squared is equal to g, and we're trying to get the spin rate. So that's going to be the square root of g over r, right? Divide both sides by r to get omega squared equals g over r. Take the square root. I'm just going to jump this up here now. So the spin rate is going to be the square root of 9.8 divided by 0.45. And as I put this on my calculator, 9.8 divided by 0.45 raised to the 0.5 power, it looks like omega is going to be 4.67. 4.67 radians per second. My wife is adding our dental appointments on her calendar. But notice that we're not interested in radians per second. We want revolutions per second. So remember that there are 2 pi radians in 1 revolution. So we're going to have to take this 4.67 and divide it by 2 pi. So 4.67 divided by 2 pi equals 0.743. 0.743 revolutions per second. All right, so that's how fast you would have to spin this thing to keep the ping pong ball from falling. Okay, so that is one problem. I'm going to do one more here. This one is, I find this one quite fun. So if you look at this picture, we have purple shirt girl. And let me highlight her for you. Purple shirt girl is right there. And you can see that there is a creepy guy with shades going to spin the kids on the merry-go-round. Right? Very creepy guy just wanders up and says, "Hey kids, can I give you a spin?" And they're rightfully a little bit worried. She's sitting on the edge of the merry-go-round, and she's got some static friction between her pants and the surface of the merry-go-round. This strange man, because he's weird, he's going to try to spin this merry-go-round faster and faster and faster until the girl flies off. That is how the problem goes. So let's just imagine. So let's just first get a picture of the physics here. I'm going to do a side view of the merry-go-round. Without getting too in-depth, because that would be creepy, this is her butt. And there. Now, if you just think for a second, as this merry-go-round spins, there is an outward force on her trying to get her to fly outward, and that is the centrifugal force. And everybody knows this force. You know, if you get on a merry-go-round and spin really fast, you feel like you're going to fly off. In fact, kids used to do that all the time. What's keeping her from flying off? Well, it is the static friction between her butt and the merry-go-round. Force of friction, and it's static friction. And you know it's so that in this case, the centripetal force, the inward directing force, is actually, instead of being tension or gravity, it's actually static friction. The static friction is the inward force, because again, if you draw this picture just from a top view, and she's sitting, let's say, right here, the static friction always points inward to keep her from sliding. And so this is I like this problem because the centripetal force is not gravity or tension in a string. It's actually the static frictional force of her pants and the merry-go-round. All right. So the object of this creepy guy is that he wants to spin it so fast that the centrifugal force cancels out the static frictional force, and off she slides. So what is happening at that moment? At that moment, the static frictional force, we're going to set equal to the centrifugal force. At the moment she slides off. The static frictional force is mu sub, sorry, not K, I was going to do K, that's kinetic friction. The static frictional force is mu sub S times the normal force. The centrifugal force, and notice it's asking how fast in radians per second, so that's omega, right? So we're going to use the mr omega squared formula for this one, simply because if you look over here, that's how they want the answer, radians per second. When I say they, I mean me. I made up this question. Clearly I made it up because it has a creepy guy in a park. It's just kind of my sense of humor anyways. On a flat surface, the normal force of an object is mg. So guess what? It doesn't matter how heavy the girl is. She will fly off at the same spin rate. Doesn't matter whether she is a a very svelte and petite, 35 pounds, or whether she is much larger number than that. It could be an elephant sitting on the end there. So, anyways, mu sub s g has to equal r omega squared, and we're interested in omega. So omega is equal to the square root of mu sub s g all over r. And now we can figure this out. So 0.34 times gravity, times 0.34 times 9.8 divided by 2.5 raised to the 1/2 power, which is the same as taking a square root. I get 1.15. So omega is equal to 1.15 radians per second. So creepy guy, all he has to do is spin all the kids at 1.15 radians per second, and off she flies